Okay, so in module 5, we are going to look at a few subsections. So the first subsections, we are going to look at system of linear equations. So I'm just going to write what we are going to look at. So we are going to look at the system of linear equations. Okay, so if you look at here, what we are going to learn here is more on linear relations. Okay, so that's the first subsection. The second subsections, we are going to look at row echelon form, and then followed by Gaussian elimination. I'm not sure whether you have covered this before or not. And then followed by matrices and matrix operations. I'm pretty sure you have covered this one, matrices and matrix operations. And then you're going to look at inverse matrix and matrix transformation, and then the application of linear systems. Okay, so this is what we are going to cover in this module 5. So if you look at this system of linear equation, this is how we replace our problems, we can say as our problem. So we replace our problems using a system of linear equations, and to solve that systems, we are going to present that in this kind of form. So this form will help us to solve our system of linear equations. So at the end of our modules, for module 5, we are going to look at some applications where we can apply a linear system in real life applications. All right. So if you have any questions regarding our course, you can text me, or you can chat or write on the chat box, or you can unmute yourself and then ask any questions. Okay, so we are going to look at what is means by system of linear equation. If you look at this, okay, systems of linear equations is consists of a linear equations. Okay, is a system that consists of a linear equations. So what it means, if we have a couple of equations, let's say we have m equations, so this could be anyway. So we have m equations in the n unknowns. Okay, so the n unknowns refer to our x. Okay, so this could be any variables. Okay, so it starts from x1, x2 until xn. Okay, so if we have this kind of situation where we have m equations in the n unknowns, so the n unknown refer to how many x you have. So you can write this as a set of linear systems. Okay, so for examples, we have our first equation. Let's say we have our first equations. I'm going to write as a11 x1 plus a12 x2 plus so on until we have a1n xn equal to b1. Okay, so let's say this is our first equations where we have this x. So we have this x is an unknown variable. So the number of x is until n, so we have until n. So in front of this x, we have what we call as the coefficient of our equation. So these coefficients can take any values, depends on what kind of problems that we want to solve. So we have coefficient A11, coefficient A12, and coefficient A1n. So the subscript here, if you look at this A11, it's referred to the location of these coefficients. And A12 is referred to this location of these coefficients. So if we are going to have another equation, so we can write as A21 x1 plus A22 x2 plus A2n xn equal to b2. So if you look at the coefficient in here, A21, A22, so you can see that the the subscript number there is changing. So that's indicate the positions of these particular coefficients. So that position is in term of, if we are going to put it this in term of a matrix form. So this is the position that indicate which is the location of this certain coefficient inside a matrix. Okay, so the rest, if you're going to write, so it would be AM1 x1 plus AM2 x2 plus AMN xn equal to BM. So this is what if we have M equation in the N unknowns. Okay, so be very careful when you write your equations so that if you look at this variable x1, they must consist of the same informations. You have x1, x1, and x1. So each of these must consist the same information. The same as your x2, they must the coefficient in front of the x2 must refer to the same things. So you won't mix up the information. All right. So as I said, the values of A here, okay, it can take any value subscript, depends on its location. This is referred to the coefficient. So the coefficient depends on your situations. So for your x1, x2, and so on, where you have xn, this is what you call as your unknown variables. This is what you're going to find, unknown variables. Okay, so this is usually what you're going to solve in your systems. So for your B1 and B2, your B1, B2, and Bn, this is the solution for the systems. So you have a solution for the systems and you want to fit what is the combination of your X in order to satisfy your solution B. That is what you're going to find. So if you think truly, if you already have the solution in terms of B, so the values that you're going to plug in your X would be would have different choices, isn't it? Okay, so the solution that you're going to plug for your x1 and xn in order to satisfy your solution, if you think carefully, you can have different options. So meaning to say that if you have a different options to satisfy your solutions, you will have a few solutions. So generally, there are three types of solutions when we want to solve this. Okay, so I give you an example. So examples, we consider two equations. Okay, so this is a linear equations. We consider a1x plus b1y equal to c1. Okay, so this is our first equation. And the second equation is a2x plus b2y equal to c2. Okay, so we have two equations with two unknowns. So our unknown here is x and y. Our solution is C1 and C2. So we're going to identify what value we're going to put inside the x and y in order to satisfy our solution C1 and C2. So the value of x and y that you can choose from will give you a different solutions. Okay, so generally there are three types of solution. The first solutions would be what we call as no solutions. Okay, so whatever value you put inside your x and y, it doesn't result to the C1. So in that case, we say we don't have any solutions. The second solutions is we have a unique solutions. Unique solutions, which means we only have one combination of x and y to satisfy our solution C. So we have a unique solution. Third one is we have what we call as infinite solution. Infinitely solution means we have multiple solutions. So which means your x and y can take different value, but at the same time it still result in C. Okay, so you have a multiple solution. So this is the type of solution that can come, or you would expect when you try to solve using a linear system approach. Okay, so if we're going to view this, usually if we have any equations, we can view them, or we can view this graphically. Okay, we can sketch this. Okay, so if you're going to sketch this for the case of no solutions, okay, so let's say you're going to sketch that. So you have x-axis and y-axis. So if you're going to sketch that, you might have a graph like this. Let's say you have your first graph like that, your second graph like this. Okay, so no matter what value you put there, these two graphs won't intersect. Okay, so this is this graphical view will tell you that there is no solution because you somehow cannot get these two graphs to be intersect between each other. So this is a no solution case. So for the unique solutions, if you're going to draw, sometimes it's easy to draw to find or to find out whether we have solution or not by drawing particular equations. Okay, so the second, if you're going to draw, let's say this is the graph for your first equation, and then for your second equation, you have graph like this. So you have the intersections between these two graphs, but the intersection is only one. Okay, so in this case, you have a unique solutions. Okay, so if you're going to put the value of your y-x, so your y towards positive infinity and negative infinity, the same as your x, somehow you only can get one intersections there. So that means you have a unique solution. For the case number 3, we have infinite solutions. So this one can take, okay, so this one can take more than one point of intersection. For examples, if we are talking about a linear systems, okay, so we have the first equation like this, okay, so that's your first graph. The second graph would be similar like this if we are talking about linear. Okay, so in here you can have your intersection here, you can have here, you can have here, and so on. So this is, you have more lines that intersect with each other. So you have multiple solutions. And in the case of nonlinear equations, you can write something like this for your first graph. And then for your second graph, maybe you can write something like this. So you have intersections at different multiple points. Okay, but this one is for nonlinear systems. Okay, but usually for these modules, we focus on linear systems. All right, so we look at another examples. Okay, so in these examples, we have a value. So we consider a linear systems that have this particular equations where we have x minus y equal to 1, 2x plus y equal to 6. Okay, so we put a value in it. Okay, so in the previous one, we just view it graphically. Okay, so now we're going to solve this to find out whether which equations this falls in which categories. So we have x minus y equal to 1. So that's our first equations, and then our second equations. So to solve these equations from 1, we can say x is equal to 1 plus y. So we put 1 inside 2. So 1 plus y equal to 6. So this one we put this is from 1. So you got 3, equation 3. So you put 3 into 2. So you have this equation. So if you solve it, you have 3y equal to 4. So your y would be 4 divided by 3. So you use this y, put it back inside your equation 1, so you can have your x. So your x would be equal to 7 over 3. Okay, so this is how it looks like when you solve mathematically. You have a specific value of your x and y. So your x and y is 7 over 3, 4 over 3. Okay, so this is the value of your x, this is the value of your y. So you have a unique solution. So in this case, you have a unique solution. So next example, we are going to look at example where we don't have any solutions. So we have the first equation x plus y equal to 4, 3x plus 3y equal to 6. Okay, so this is example where we don't have any solutions. So again, this is your first equation, this is your second equation. So from 1, you can have, you can have x4 minus y. Okay, so from 2, you can have 3, 4 minus y plus 3y equal to 6. So here you got 12, 3y plus 3y equal to 6. Okay, so negative 3y plus 3y, you got 0, isn't it? So 0, 6 minus 12, you got 0. So you have this at the end. So what this tell you that if this 0 is the equations on your left-hand side is equal to the equations on your right-hand side, so this doesn't tell you anymore, isn't it? Because you cannot get the 0 equal to negative 6. So in this case, we said this is a system with have no solutions. Why is it no solutions? Because by solving this mathematically, you get these equations where you don't have the equation left-hand side, which is not equal to your answers on the right-hand side. So we have a no solution case. Okay, this is if you're going to solve it mathematically. So another example is solutions that have infinite or have many solutions to it. So we look at the example of that. So we have 4x minus 2y equal to 1. Okay, and then 16x minus 8y equal to 4. So you got your first equations and then you got your second equations. So we solve this as before. So from 1, we have 4x equal to 1 plus 2y. So if we're going to move 4 to here, so we have x equal to this equation. So we put this equation, let's say this is equation number 3. We put inside number 2, so we have these equations. Okay, so you have 4 plus 8y minus 8y equal to 4. And then if you solve it, you got 0y. And then here also you got 0. Okay, so in this case, we have this is fine because your left-hand side of the equation is exactly the same as your right-hand side of the equation. So this is fine. So next, since if we solve, we got this equation 0, 0. So that means if we take from 1, okay, if we take from 1, or you can take any from 1 or 2, if from 1, we have 4x minus 2y equal to 1. Okay, so meaning to say these equations can take any values of x and y. There is no a specific solution to it. Okay, so the solutions can take any values as long as it is result in 1. Okay, so in this case, we have a multiple solutions. Okay, so this is how you're going to spot if you solve it using mathematically. So your x and y here will take any can become from any combinations that will result equal to 1. Or if you take from equation 2, your x and y also can take any combinations that will give you equal to 4. So you have a case where you have a multiple solutions. Okay, so once we know that generally we have 3 types of solutions, okay, so we're going to look at back our problems. Okay, so our problem just now is can be represented in this particular systems. We call it as a system of linear equations. So the next question, if we have equations that is more than 2 and unknowns that more than 2, because in previous example we only have 2 equations and 2 unknowns, so we can solve it quite easily. But if we have a much bigger equations that can consist more than 2 unknowns and 2 equations, then it will become a bit difficult to solve it using our previous method just now, where we put it in different equation and we sub each of these equations. So another way to solve this another way to solve this system of linear equation is by represent them in a matrix form. Okay, so the matrix forms that we're going to create is called as augmented matrix. Okay, so this augmented matrix is just simply represents your system of linear equation into a matrix forms. So if we're going to represent this in a matrix forms, let's say this is our matrix. Okay, we start with the first equations. We have A11. So your A11 would be your coefficient at the first location, which is row 1 and column 1. Okay, so this is what we put for our x1. Okay, so this part is for the x1. So this row is for the x1. And for the second equations, we have A21. So A21 is a coefficient that located at row 2, column 1. And then so on until we have a coefficient that located at row M, column 1. Okay, so this is in terms of matrix. So for the x2, we have the coefficient that located at row 1, column 2. And next is row 2, column 2, until you get AM, column 2. Okay, so this ones could be any until you got A1N, A2N, and then AMN. Okay, so MN is the size of your matrix. If you have 5M and 5N, so you can expect your matrix to have a size 5 times 5. And next, you can see that the result B1, B2, and Bm, we're going to combine this result inside our matrix as well. So we have B1, B2, and Bm. Okay, so this matrix is what we call as augmented matrix. Okay, so what this matrix does is it helps us to solve this, to solve this x1, x2, and then we have xn. Okay, it helps us to find these values. But before we find these values, we need to put our system of linear equation into augmented matrix. So once we put to become augmented matrix, then we can use a certain methods. Okay, so we can use what we call as a Gaussian elimination method. Okay, so I give you examples. Okay, examples we have this system of linear equations. We have 3 equations, x plus y plus 2z equal to 9, 2x plus 4y minus 3z equal to 1, 3x plus 6y minus 5z equal to 0. So consider we have this system of linear equations is already put in such a way. Okay, so we need to solve it. So to solve it, we use what we call as a Gaussian elimination method. Okay, but to use the Gaussian elimination method, you need to put this into augmented matrix. Okay, so if you put augmented matrix, this is your x. So your x is 1, 2, and 3. Your y is 1, 4, and 6. And your z is 2, -3, and -5. Sorry, don't forget your b, which is your result, which is 9, 1, 0. Okay, so this is augmented matrix. So if we're going to solve this, we're going to find what is our x, y, and z. We use a Gaussian elimination method. So what is our goal from this matrix? Our goal is to transform this matrix to become 1, 0, 0, 0, 1, 0, 0, 0, 1. So you can see that the coefficients here from our augmented matrix is transformed to become as identity matrix, isn't it? We have ones on the diagonal lines. So we call this as a diagonal line of our matrix. So we have 1, 1, 1. So this whole matrix from the coefficients of augmented matrix will become identity matrix. So that is our goal. So our result would be x here, y here, and z here. So it can take any forms. So this would be our solutions to our problems. So how to perform Gaussian elimination method? It can be summarized into 3 steps. The first steps we can replace, okay, so this is the summary of operations that we can perform when we want to apply Gaussian elimination method. So the step that you can perform, the first one is you can replace n equations by multiply both sides by a non-zero constant. Okay, so this is the first steps, one of the steps that you can do. So another step that you can do, we will look at this when we solve these problems later on, but this is just a summarize. So the second step that you can choose is by replace n equations by the sum of itself and a multiple of another equation. Okay, so this is another steps that you can do. And the last steps you can do, you can swap the positions of 2 equations. Okay, so you can have 3 different steps, we can call it as a steps or operations, 3 different operations to perform your Gaussian eliminations. Okay, so if you look at this, since you have the operations, you can actually write this in a code, okay? Write this in programming codes and you can construct you can develop your own code to perform Gaussian elimination method. So you can do this using programming language. Okay, so we come back to our equations we got just now, where we got this 1, 2, 3, 1, 4, 6, 2, negative 3, and negative 5, 9, 1, 0. Okay, so let's define first how many row we have. So this is our row 1, this would be our row 2, this would be our row 3, and this is your column 1, column 2, column 3, and then you have a column 4. So again, your objective just now, you want to make this one to become this identity matrix, and the result can take any values. Okay, so we start with the first row, and column 1, row 1, column 1, you have this one, so it match with our objective, so that's fine. So you move to another row, which is 2, row 2, column 1. So this part, you need to change it to 0. So to do that, you can choose any of the 3 operations. Okay, so we can say, okay, so let me write here. So row 1 is fine, we just write back. So this is our step 2. So row 1 is fine, we can just write it back. But row 2, we need to change 2 to become 0. So maybe we can set, or maybe row 2 plus with row 1, but row 1 need to multiply with negative 2 first. Okay, so if row 1 multiply with -2, so this one will become -2, and 4 will become -8, and 3 will become negative, 2 will become, sorry, this one should be, because we multiply row 1 with -2, so this one also -2, and 2 will become -4, and 9 will become -18. Okay, so you add that with row 2, so you get this 0, and then you get this 2, and you got this -7, and you got this -17, isn't it? Okay, so you change this to become 0. So for the next row, row 3, you can just write it back. 3, 6, -5, 0. So it's a good approach. At one steps, we only perform one operations. Sometimes you can perform two, but make things follow the procedure, because if sometimes you perform two operations at one steps, you might mess up with the rest of the coefficients. So it's always a good thing. We focus only one operations at one steps. Okay, so since that is done, the next operation is we move to another row, which is row 3 and column 1. So we move to here. Okay, so if you move to 3, you can write back your row 1 and your row 2. Okay, so how to change your row 3 again? You can use any row. Okay, so in our case, we use row 1, because if you use row 2 here, it's 0, so you cannot change 3 into 0. So what you can use is you use row 1, but you need to multiply with -3. Multiply row 1 plus with row 2. Okay, so your row 1 you multiply with -3, you got this -3, and this one also -3, this -6, you have this -27. Okay, so that should change this one to become 0, this one 3, this one -11, and this is -27. Okay, so you have these two become 0. All right, so far so good. Okay, so next we can move to the next column. Okay, so our column 1 is settled. So next we move to the column 2. So inside a column 2, you can choose whether you want to make this 1 become 0 or this 3 to become 0. But noted that our diagonal line, this is 2. Okay, so maybe it's a good idea we start with this one first, because that is easier. So we want to change the diagonal line to become 1, isn't it? That is our target. So we want that to become 1. So we have our row 1 and our row 2. So this one we didn't change first, so we just write it back. So we're going to, sorry, this is row 3, this is row 2. So we're going to change these 2 to become 1, so we can multiply by a constant. Okay, so we multiply 1 over 2. So that one give this to become 0, get 1, get -7 over 2, and -17 over 2. Okay, so you can see that this one already become 1. So next, you can choose either you want to do this 1 or this 3. Okay, but if you're going to write a code in here using a programming language, it might be easier to start with number 3 first, because you just move to one column, but you still retain in the same row. But you can choose one also. But just to illustrate that, if we're going to write this in a programming code, it's easier to just move to another column by retaining the same row. So because of that, we're going to change this 3 to become 0. So our row 1 and row 2 is didn't change, so you can just write it back. Okay, but your row 3 will change. Okay, so how are we going to get this 3 to become 0? So we can choose either we want to use row 1 or row 2. But if you look at row 1, you got this is 1, isn't it? So if you choose row 1, your 0 in here and row 3 column 1 might get affected. Okay, so it won't be a good idea to use row 1. So what you can do is you choose row 2. Because row 2 here you got 0, so it won't affect your 0 at your row 3 column 1. Okay, so we can say that we're going to use row, for this part, we're going to use row 2, but we need to multiply with negative 3, multiply with row 2 plus with row 3. Okay, so this one will give you 0, because this is also 0. And let me write here, this is 0, this would be negative 3. So negative 3 plus 3, you got 0, isn't it? And here, negative 7 over 2 multiply 3, you got positive 21 over 2. And then plus with negative 11. Okay, what do you get here? You need to use calculator. Okay, so I think you got, let me check first. Okay, so if you use calculator here, you will got 1. Okay, you got the ideas of performing this part. And then for the next column here, you will get, 3, isn't it? Okay, so you can perform this using your calculator. Okay, so you got 0, 0, 1, and 3. So you got this one settled. Okay, so next we're going to look at the next row. So the next row would be this one, isn't it? So your row 3, 0, 0, 1, 3. So your row 2, 0, 1, negative 7 over 2, negative 17 over 2. Okay, so we didn't change anything on row 3 and row 2, but on the row 1s, we need to replace the coefficient inside row 1 column 2 to become 0. Okay, so what we can do, we can add row 1 with row 2, isn't it? Because inside your row 3, you already got this 0, so you might not be able to change it to 1. So you need to use row 2. So the row 1 you can perform, you add negative 1 multiply with row 2 plus with row 1. So this is what happened inside your row 1. Okay, so if you do that, this one you will return 1 because you multiply with 0 plus with 1, so you got 1. And this one, 1, negative 1 plus 1, you got 0. And here you got 11 over 2. And here you got, so here you got 35 divided by 2. Okay, so you got these equations. So the next steps, we want to change this one to become 0. So your row 2 and row 3 is 0, 1, negative 7 over 2. Okay, in here, I think we can perform both of it. Okay, so row 1 is returned. So in here, row 2, we can change this one also to become 0. Okay, so we're going to use this row 3. Okay, so row 3, for the row 1 here, hopefully you're not confused. For the row 1s, we are going to perform negative 11 over 2 multiply with row 3 plus row 1. Okay, because this is 1, this is 0. So if this one we change to negative 11 over 2, then we can change this to become 0 without affecting this 1 and 0. Okay, and for the row 2, we're going to multiply 7 over 2 to row 3 plus row 2. Okay, so this one, negative 7 over 2, we're going to multiply 1 with positive 7 over 2. So if we add them, it will become 0. So this is the case where you can perform two operations in a single steps, okay? But this, you need to make sure that it doesn't affect the rest of the coefficients. Okay, so if you do this, your row 3 is retained, 1, 3, and your row 2 will become 0, 1. So this one will change to 0. And this one, if you solve it, it becomes 2. And for the row 1, you have 1, 0. And this one changes to 0. So if you solve it here, you become 1. All right? So here you can see that this is what we aim for, where you have your coefficients will become identity. You have this 1, 1, 1. So you have this diagonal lines is of 1. So the rest would be 0. So this part where you have your solutions. So your x would be 1, your y would be 2, and your z would be 3. So you have a unique solutions. All right, so what we call this matrix, we call this matrix as a reduced row echelon form, ref. Okay, so you have your augmented matrix just now. You want to transform your matrix to become a reduced row echelon form matrix. And to do this, you are going to perform Gaussian eliminations. And the Gaussian elimination got 3 operations, what we described just now. Okay, so the whole things you can configure using a programming language. But you need to understand how these forms looks like, the reduced row echelon forms. Because some metrics, okay, some metrics you might end up you might not be able to get this identity matrix. Okay, so some problems, if you use Gaussian eliminations, you won't be able to get a very nice identity matrix. Okay, but that doesn't mean that you haven't solved the problems. You still can solve the problems without having this identity matrix. So there is a few properties when we talk about this RREF. There's a few properties that can help us to set that, okay, we have come to our stopping point because we already have this kind of matrix. So that matrix is indeed a ref matrix. So what property is that is the first one, if a row does not consist entirely zeros, so then the first non-zero number in the row is 1. So we call this a leading one. Okay, so I give you examples. So let's say we have a matrix, we have 4 equations with 4 unknowns. Okay, so if you have 4 equations with 4 unknowns, after you apply Gaussian elimination method, in the end, the best you can get is this kind of matrix, this kind of forms. Okay, so the solution will be 1, 3, 0, and 0. Okay, so after you try apply Gaussian elimination methods, okay, from the augmented matrix, so whatever you try, the best you can get is this kind of forms. So this would be your final solutions, okay? Consider this would be your final forms. Okay, so we're going to use the property of RREF to set that, to verify that this is a final form. So the first property if a row does not consist entirely of zeros, okay, you don't have this very nice identity matrix because you got 1, -2, and 1 here. So it doesn't consist entirely of zeros. Then the first non-zero number in the row is 1. Okay, so if we're going to look at this row 1, this row 2, and then row 3, and then row 4. So for the row 1, the first non-zero number would be 1. Okay, you got 0, you got 1. For the row 2, the first non-zero number, you got 0, you got 1, would be 1. Okay, so that's to show that, okay, this is a ref, RREF. So you got here 1 and 1. For the row 3 and 4, is fine. You got all 0, so that's fine. So the 1 in here, we call it as a leading 1. Okay, so that's the first property telling you that you have achieved your ref form, your RREF forms. So the second, we call it as a property. If there are any rows that consist entirely of zeros, so then they are grouped together at the bottom of the matrix. Okay, so what this means, if you look at your R3, row 3 and R4, all the coefficient in here is 0, isn't it? So they are grouped together. Sometimes you can have this R3 is located inside your R2, and then your R2 is located inside your R3. Okay, so if you have that case, you cannot say it's in ref form. So what you can do, you can swap this different row. Because why do you need to swap? You want to group all rows that consist of entirely zeros, group them together at the bottom of the matrix. By then you can achieve these final ref forms. Okay, so you might have the case like that. And the third properties, so in any two successive rows that do not consist entirely of zero, the leading one in the lower row occurs further to the right. Okay, so the number three properties saying that if you have two successive rows that not consist of entirely zero, so in our case we have row 1 and row 2, then the row 1, the ones on top of it, must, the one on, if we're going to look at this, the ones in the lower row occurs further to the right than the leading one in the higher row. So you got your leading one here for the row 1, and you got your leading one here for the row 2. Okay, so the way you group them together, if you group row 1 and row 2, you need to make sure that the leading one on the top of the matrix is located furthest to the left. Okay, so this one located furthest to the left compared to the leading one on the row at the bottom of row 1. So the leading one at the bottom of row 1 must be placed furthest to the right. Okay, so if this is the other way around, so what you need to do is you need to swap them before you can claim that you have finally reached your ref forms. Okay, so this is three important properties. Okay, you need, that will tell you that you have reached your final form of RREF. Sometimes you try so many time operation also you cannot get this identity matrix. So that's fine. So you can use this to show that you have reached your final forms. And there's one more, the last one, which is number 4, is each column that contains a leading one has zeros everywhere else in that column. Okay, so each column that content of leading one, okay, so we have here column 1, this is column 1, this is column 2, column 3, and column 4. Okay, so this is fine. So if you look at the one that consists of this column 5, the one that consists of leading 1, under it will be consist all of 0. And for the column 4, you have a leading 1, under it will be consist all of 0. Okay, so there's another way how you tell that you have reached your final forms. So otherwise, you haven't reached your final form yet. But okay, there's another one. So let's say you only achieve your properties 1. Okay, it's only valid for your first property, second property, and the third property. It doesn't achieve the fourth one. Okay, you can still claim that you have achieved your final form, but that form is called as a raw echelon form. Okay, so you have two forms. So the first one is reduced raw echelon form. Okay, so usually this is denoted as RREF. So the second one, you have a form where we call as a raw echelon form. So both also a solution. Okay, so the difference is for the RREF, you achieve both the property 1, 2, 3, and 4. But for raw echelon forms, you only achieve property 1, 2, and 3. So the number 4 you didn't achieve, but it's still a solution to it. Okay, some problems you only can achieve this 1, 2, and 3. So either one is a solution to your problem. So if you have a augmented matrix, if you can put it nicely in a identity matrix, so it would be very good. But if you can't, you can reduce until you achieve either RREF, or you can reduce until you achieve raw echelon forms.